Today we're going to talk about sections 5.7 and 5.8. Rational functions. A rational function is a function that's in this form, where you have the function equals p of x over q of x. P of x and q of x are polynomial functions. Simple rational functions. Getting ready to graph. So the question here would be, given a simple rational function, we want to graph this. So we need to state the domain and range, start by stating the domain and the range. For this particular function, it is not defined if the denominator is 0, which means that x cannot be 0. So it's undefined when x is equal to 0. These tables show you what happens as the function gets closer to 0 from the left-hand side, or from negative infinity, and from positive infinity, meaning that from the left and the right-hand side of the function, what the value looks like. So if you take the point negative 0.1 and then get a little bit closer to 0 at negative 0.01, and then get a little bit closer to 0 at negative 0.0001, this is what the function's value is. Similarly, on the right-hand side of 0, if we pick values that are increasingly closer to 0, we get the following table. So if we start with 0.1, we get 10. If we get a little bit closer to 0 and go to 0.01, the function's value is 100. And if we get even closer to 0 at 0.0001, the function's value is 100,000. So what's happening is as you're getting closer to 0 on the right-hand side, the function is increasing very rapidly. On the left-hand side of 0, as you get closer to 0, the function is decreasing rapidly. So the way that we could describe this behavior using symbols would be the function approaches negative infinity, that's my y behavior, my vertical behavior, as x approaches 0 from the negative side. That's what that negative means. Similarly, based on our right-hand table, we could say the function approaches infinity, because it's getting infinitely large, as x approaches 0 plus, which tells me that x is approaching 0 from the positive side, or from the right side. The following tables are just a copy of the first tables. Using the information from those tables and picking some additional points, you can obtain the graph. So we have all the points from those two tables, the 6 points, and then we select some additional values. Remember my rule, you want at least 5 points. For rational functions, you're going to need more than 5 points, right? You're going to want at least 5 points for each part of this rational function. So make sure that you're smart in where you're selecting your points. You want to make sure that you have an equal number of positive and negative points. Make your table of values. You can also use your calculator to have it give you the table function, and then you can look up your values and plot your points, connect your dots, and you have your function. The arrow notation that I was discussing before, just to review that, the first symbol says x approaches a from the left. All right, that's what the little negative sign tells us. The second one is x approaches a from the right, meaning from positive infinity. You can think of it as positive infinity is on the right-hand side, so you'll see the little plus sign. X approaches negative infinity means that x is going towards negative infinity. It's getting increasingly large. in the negative sense of the term. It's getting small, getting the negative number is getting more negative. And then x approaches infinity is saying that as x is getting larger, it's increasing without bound. Or you can say it's approaching a very large number. For the last example, we said that x could not be equal to 0. That was a hole in the graph. In this case, because as you approach it from the two sides, the value is increasing towards infinity or decreasing towards negative infinity, that we refer to as a vertical asymptote. You might remember from high school that asymptotes are invisible lines that a function approaches but never quite gets there. So you won't cross your asymptote. But as you get infinitely closer, you'll see that the distance does close and close and close. And so it almost looks like you will intersect the asymptote, but you won't actually get there. Here's a definition for vertical and horizontal asymptotes. The line x equals a is a vertical asymptote, and as you can see, this graph of this function, as x is getting smaller, it's approaching a, but it will never actually cross a, and that works on both of these, whether I'm approaching from the left or approaching from the right. And down here we have a horizontal asymptote. All right, you can see as x is approaching positive infinity, I'm moving from left to right on my graph, I am approaching this horizontal line. Just like my vertical asymptote, I will approach that line and get closer and closer, but I'm never actually going to touch it. And we're looking at end behavior. So now you might say, well, we did cross it here, but that's because it wasn't the asymptote there. This is on left-hand behavior. So as x gets infinitely small, y approaches b. Which was my asymptote. We talked about transformations of various types of functions, so let's look at transformations of a rational function. We have our simple rational function, 1 over x, which is a rational function in the form ax plus b over cx plus d. We can graph that transformed function by shifting, stretching, reflecting the graph that we started with for the rational function. So let's look at example 2a. The original function is f of x equals 1 over x. That's our rational function. We can express that in terms of r for f as follows. So we've got 2 over x minus 3, and then we can factor out the 2, meaning what's left, we have 1 over x minus 3, and that is the function evaluated at x minus 3. And you might say, where did that come from? Well, our function is 1 over x. And so essentially what we've got here is 2 times our original function 1 over x, but in this case, x is not just x is x minus 3. So that is a horizontal shift. So our original function, we had an asymptote of x equals 0. And so if we're shifting 3 units to the right, that means we now have a vertical asymptote of 0 plus 3, which is 3. So if we already had the function graphed for 1 over x, we could transform those points, meaning shifting them all over. So you would have your 10 points that you used to graph the original transformation, the original function, and then you would add 3 to each one of those x units and move it over. The y value would remain constant. And then the output, because we have the 2 here, means that each one of those values of y would then become twice as large because it's also being stretched. If we look at B, it's a little bit more complicated. All right, so we start by looking at how we can break this down. And if we break that into parts, we can write, using long division, we can get 3 minus 1 over x plus 2. And then we can rewrite this so that it's in the form minus f of x plus 2 plus 3, which shows that we have a horizontal shift, a vertical shift, and a reflection. So once again, we would start with our original graph of 1 over x and perform those transformations on each point. Remembering that we use PEMDAS, so we work from the inside out, so that means that we would start with the x plus 2, so we do the shift, and then we would do the reflection, and then the last thing we would do would be to raise each one of those points up 3. So how do you find asymptotes of rational functions? So here's our rational function. Remember that the numerator and the denominator are both polynomials, so this is just showing you standard form of those polynomials. Vertical asymptotes are going to be the lines x equals a, where a is the 0 of the denominator, meaning that we can't exist there, right? It's outside of the domain. So the first thing you want to do is find your domain, and that will tell you where the function does not exist. Those will be your asymptotes. If n is less than m, right, so you're looking at the highest power in each polynomial. If your numerator polynomial is less than your degree for your denominator polynomial, that means that there's a horizontal asymptote of y equals 0. If n is the same as m, that means that r has a horizontal asymptote of y equals a n over bm, meaning you're taking your leading coefficients from your numerator and dividing by the leading coefficient of your denominator. And then if n is greater than m, then r has no horizontal asymptote. So you're going to want this on your cheat sheet for this test. So here's an example of finding those asymptotes. So here's our function. It's a rational function. And it makes sure that you order these, right? Highest power to lowest power, both in the numerator and the denominator. To find the vertical asymptotes, we need to factor because we have to figure out where the denominator is equal to 0. So we factor the denominator. And we see very quickly, if we set this equal to 0, we would get 1/2. If we set this factor equal to 0, we would get -2. The vertical asymptotes will then be x equals 1/2 and x equals -2. So you take the two zeros and you set them equal to x, and that would be the vertical lines that are the asymptotes. Finding the horizontal asymptote, you look at the degree for the numerator, right? So the highest power is going to be a 2, so that's going to be a degree 2. Our denominator, I'm sorry, the numerator is degree 3, and our leading coefficient of the denominator is 2. So that gives me my, oops, because they're the same power, I take my leading coefficient for my numerator and I divide by my leading coefficient for my denominator. And so that gives me y equals 3/2 for my horizontal asymptote. So I would graph each one of those asymptotes, and then I would select points on either side of those asymptotes in between until I could graph. If you're going to confirm what your graph looks like using a graphing calculator, you want to make sure that you select dot mode. Otherwise, you end up with some really weird lines. Finding asymptotes of rational functions. Here's another example. So given this function, we need to first find, and we want to state its domain and range. We need to factor the denominator, just like the last example. So in this case, it's x minus 2 times x minus 2, or x minus 2 squared. So that means we have a vertical asymptote. We set x minus 1 equals 0. So that means x cannot equal 1. So our vertical asymptote would be x equals 1. And then we want to pick some values approaching 1 on either side. Okay, so picking some values. Here we're starting at 0. We're picking values that get closer and closer to 1. So the ones that the book selected was 0, 0.5, 0.9, and 0.99. You plug them in and get what the y values are. So you can see that as x is approaching 1 from the left, we are getting larger rapidly. We do the same thing on the right-hand side. So as x is approaching 1 from the right-hand side, meaning I'm getting closer and closer this way, so I start at 2, and then I pick a value that's closer, maybe 1.5, 1.1, 1.01, right? You want to be really close to 1 without being at 1. Okay, what happens to the outputs? Similarly, as I approach 1 from the right-hand side, my y value or my output is getting large quickly. So that means that my end behavior looks like this. And I would plot those points. So that's just part of the graph. We need to continue to find our horizontal asymptote. So the horizontal asymptote, as you look at this, you have your fractional expressions, 1 over x, 4 over x, 5 over x squared, 2 over x, and 1 over x squared. Those all approach 0 as x goes towards positive or negative infinity. So in these terms, they approach 0. So the horizontal asymptote is going to be 2. So that gives me my 2. And now I've got my horizontal and my vertical asymptote. Talking about our domain and range, and then you would grab some additional points to show how it approaches 2. And plot them and connect your points to get the rest of your graph. For domain and range, the function r is defined for all values of x other than 1. That's where our hole is, because that's where our asymptote is. So our domain would be all values for x, all real numbers except 1. And then from the graph, we can see that our range is all values greater than 2, because 2 is our asymptote. So graphing rational functions, how do we do it? We factor the numerator and the denominator. We find intercepts, just like we would when we're graphing our polynomials. Finding zeros. The zeros will tell us where our vertical asymptotes are, because they're holes in our graph. We want to look at the values of the function as they get close to those asymptotes from the left-hand side and from the right-hand side. And then we find our horizontal asymptote, if there is one, by using the procedure that we talked about back 3 slides ago. And then we take all those points and we can sketch our graph. So it's a little long. I wouldn't put a lot of these on the exam, but you certainly should be able to graph rational functions as part of this course. Here's another example. So we want to graph this function, and we want to state what the domain and the range is. So first we're going to start by factoring. So we factor the numerator and we factor the denominator. Then we're looking for where are the x-intercepts. Those are our zeros. So where does this function have a 0 in the denominator, meaning that that would be a hole in our function. We've got, if I set this first factor equal to 0, I get x equals 1. If I set the second factor equal to 0, I get x equals x equals 2, excuse me. Find your y-intercepts as well. You substitute in x for 0, and that gives you your y. Then you have your vertical asymptotes, as I said, at 1 and -2. And then we want to do our behavior near the vertical asymptote. So that means you need to approach x equals 1 from the left and from the right. So that means we're going to pick values that are close to 1 and then get closer. And then do the same thing with -2. So make a table of values to determine what your end behavior is. So as we approach 1 from the negative, you can test some values to see what happens. And in this case, they picked 0.9. So by plugging in 0.9, they can tell whether or not the output is positive or negative, because that's going to be what the end behavior is. And then you do the same thing from the other side. Pick some test values. So pick a value that's greater than 1, say 1.1, plug it in, and you end up with negative and positive. So that means your end behavior from the left is going to be approaching negative infinity. The end behavior on the right is going to be approaching positive infinity. And then you would do the same thing with the -2. So as you're approaching -2 from the left-hand side, when you plug that in, you're approaching negative infinity because your output here is negative. As I approach -2 from the positive side, I get a positive number. So that means that I'm approaching positive infinity. That's what this table is showing you. Horizontal asymptote, you're looking at the degrees of the numerator and the denominator. So the leading coefficient, you end up with, they're both the same. So n equals m, which means that we can take the leading coefficient from the numerator, which would be 2, and my leading coefficient from my denominator, which is 1, and I get 2 divided by 1 equals 2. So the horizontal asymptote for the line is going to be the line y equals 2. And then we can use all that information from up above in the tables to plot the points and then connect your points and get your graph. You will have to add some additional points to fill in your gaps, right? So you know what the end behavior looks like here, and here, and here, and here from our end behavior tables. We know our asymptotes, so we know that our end behavior here is going to approach that, and same thing here. And then we need some additional points. So you'd pick some points in this area, some points in this area, and then some points to the right-hand side so that you can adequately graph and capture what that function looks like. All right. So rational functions, as I said, you have polynomials in the numerator and the denominator. One thing that I may not have mentioned is that p and q, the numerator and the denominator, do not have common factors, meaning that there isn't something that divides into both of them. So you would want to simplify. You can cancel the factor, but only for those values of x for which the factor is not 0 because division by 0 would be not defined. So let's take a look at that. So if I look at a here, we've got x minus 3 and then x squared minus 3x. If I factor my denominator, I see that I actually have a common factor of x minus 3 in the numerator and the denominator. And so I can rewrite that as 1 over x for all x's not equal to 3. And the reason that it can't be equal to 3 is because x minus 3 would be 0. And so that actually means that we would have an asymptote there. So this graph, which is easier to graph, is going to be the same graph because it's the same graph with a factor added in. But it would have a hole at x equals 3. If I look at the second example, x cubed minus 2x squared over x minus 2, if I factor my numerator, I see that I actually have a common factor. It's x minus 2. So I could graph the simpler function of x squared, knowing that x cannot equal 2 because my denominator cannot equal 0 from my original function. And so I could go ahead and graph the function, the resulting function that's simpler to graph, but I would have a hole in my graph at those points where I said that it didn't exist. Slant asymptotes. We talked a little bit about end behavior already, but slant asymptotes, if we're given a rational function in which the degree of the numerator is 1 more than the degree of the denominator, we can use the division algorithm to express the function in this form. All right. So basically, this is as if you had done your long division or your synthetic division. You can use that as the algorithm. So R, we have a degree of R is less than the degree of Q here. And that A cannot equal 0, otherwise this leading term would drop out. So that means that as x approaches positive or negative infinity, the rational function is approaching 0. So for large values of x, the absolute value of x, the graph approaches, the graph of y equals r of x approaches the graph of the line y equals ax plus b. In this situation, we say that y equals ax plus b is a slant asymptote. Another name for that is oblique asymptote. Not everything will obviously have one of those. Only if your degree is 1 more in your numerator. So here's an example. A rational function with a slant asymptote. How do I know? Because when I look at my degree of my numerator, it is 1 more than the degree of my denominator. So how do I do this? I'm going to first factor. So I'm going to factor my numerator. There aren't any common factors, so I can't simplify. But from this, I know that my x-intercepts are -1 and 5, which I'm getting from my numerator. My y-intercept is 5/3, because when I plug in 0 for x, I get 5/3. And then my vertical asymptote is where my denominator would equal 0, so that gives me x equals +3. So once I identify those key parts of my graph, I then want to talk about what happens as I approach my vertical asymptote from the left and from the right. So as I approach 3 from the left, what's happening, if I pick some values, I see that the y value gets much larger. Okay, so that's going to be positive end behavior, right? As I approach from the negative. And then I do the same thing from the positive. And I find that y gets infinitely smaller as I get closer to 3 from the right-hand side. And then for horizontal asymptote, there isn't any because the degree of the numerator is greater than the degree of the denominator. So, but I do have a slant asymptote because I have 1, right? It's off by 1 degree. So since the degree of the numerator is 1 more than the degree of the denominator, the function has a slant asymptote. And so I use that algorithm. So I get x minus 1 minus 8 over x minus 3, and the slant asymptote would be this portion right here, which is my x minus 1. So we use that information and we plot all those points in addition to picking some additional points here in this area here and this area here. You plot the points. This line right here is the slant asymptote. So you do have to graph that as well. So when you're graphing these, you have to graph any horizontal, vertical, and slant asymptotes, if they exist, as well as determining your end behaviors and selecting some additional points that will round out your graph. All right. You might remember we talked about solving inequalities back a couple chapters ago. So extending this to our polynomials, how do we solve polynomial inequalities? We move all the terms to one side. We write the inequality so that all non-zero items appear on one side of the inequality symbol. And then we factor the polynomial. So we've got 0 on one side, factor the polynomial, and any irreducible factors. And then find the zeros, the real zeros of the polynomial. Then find your intervals. You might remember we did that, right, with our plus. We're going to do our pluses and minuses graphs, sign chart. Make a table or diagram to test those values, right? So once you find those intervals, you're going to pick a test point in each one of those intervals. And then test those by solving the inequality and make sure that it's true. Making sure that you pay attention for whether there's an or equal to in there so that you can state your solutions. So let's do an example of this. So given this polynomial inequality, we're going to first move everything to the left. So I'm going to subtract 13x from both sides. And your result is here. All right. Then I'm going to factor the polynomial. So I'm looking at this section here. All right, using the different ways that we've learned to factor the polynomials. Your end result is that. And then your zeros would be where each one of these sets of parentheses, these binomials, equals 0. So this would be x equals 2, x equals 1/2, and x equals -3. And then we look at the intervals defined, determined by the zeros. So here's my 3 zeros, and so my intervals are going to be to the left of the smallest value, in between the smallest value and the middle value, in between the middle value and the highest value, and then to the right. Right, those are my intervals that I'm looking at, the regions that I need to evaluate. Remember, the book does it one part at a time, but you could just go straight to this and plug in. So what you're doing is you're picking a test value to the left of -3 and saying, is the sign positive or negative? So if I pick, say, -4 and I plug in, I find out that it's negative. I pick a value between -1 and -3 and 1/2. Maybe I pick 1. I plug it in. So that's plus, plus, plus. So that's going to be plus. I pick a value between 1/2 and 1. And I get negative. I pick a value greater than 2. Maybe I pick 3. I plug it in, right? Plus, 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 and I end up with positive number as an output. So this tells me what my output is, whether it's positive or negative. And then I'm only looking for the values that are greater than 0. So I would only pick the positive values. So it would be here and here. So what that's telling me is that I can only have values between -3.5 inclusive, because I do have an or equal to, or it's going to be values greater than 2. Okay, so those are my intervals. I can write it out this way, saying it's this and this, or I can write it using set notation, which is I'm looking for values from -3 to 1/2. The brackets tell me that I'm inclusive, union from 2 to positive infinity. All right, here's another. Now we're looking at, rational inequalities. So the last one was polynomials, rational inequalities. Similar process. We're going to move all the terms to one side. We're going to factor the numerator and denominator, find the intervals, make the table. You're looking for sign once again because it's an inequality, and then solve. You only want to return the values that satisfy the inequality. All right, so if I had this inequality here, all right, everything's already on the left-hand side, so I don't have to do anything there. So I can factor. So I factor the numerator, I factor the denominator, and I'm looking at where are those interval points going to be. All right, so my interval points are going to be, they're going to be where each of these equals 0. So that's going to give me 4 points. Okay, so +3, +1, +5, -1. And so I come over here and I make my diagram. I'm now looking at what happens anywhere to the left of -1. What happens between 1 and -1, sign-wise? What happens between 1 and 3? What happens between 3 and 5? And then what happens to the right of 5? So I pick a test value in each one of those intervals, and my results would be plus to the left, minus in between, plus in between there, minus between 3 and 5, and positive to the right of 5. Now I go back to my original inequality, and I'm looking for values greater than or equal to 0. So that means I'm looking for positives, or 0. So that means it's going to be values to the left of -1, between 1 and 3, or to the right of 5, inclusive. And then I would graph. And that finishes up Chapter 5. So we'll review in class, and we'll set the test date. Hope you all have a great weekend.